Okay, good morning, everyone. All right, today I wish to wrap up superposition. That would be the end of all the analysis techniques for chapter 2. And then I will introduce the topic of equivalent circuits, or Thevenin and Norton equivalent circuits, which is not an analysis technique. It is simply the application of all the techniques to a larger theorem. Okay. Superposition homework has only 2 problems, but I will make it due on Monday. So Friday, Saturday, Sunday, Monday, almost 4 days to do 2 problems. Quiz as usual on Monday. Topic under assessment is mesh current analysis, but there will be conceptual questions about superposition. So again, not solving an entire circuit, but just have to show me how you will apply superposition. Okay. So let's get into our last and final analysis technique. Okay. So superposition principle states that if we have a circuit with more than one source, we can break up the circuit into individual parts, smaller parts, analyze each part independently to find a specific voltage or current present in the circuit. So if you have n number of sources, you break up the circuit into n number of pieces. You analyze each piece independently. You redraw the circuit for every single source. You analyze the circuit independently. You find the voltage or current of interest. And then at the end, you add up all of those voltages and currents. Okay. If we wanted to find a specific voltage for one single resistor, let's say VRA. Okay, VRA, for instance, and you had 3 sources in there, then you would analyze the circuit 3 times, find VRA for each source acting independently. Then at the end, you would take those 3 quantities, you would add them up, and you would obtain your actual resistor voltage, VRA. And you would have to do this for every single voltage and every single current that is present in the circuit. Okay, so if you have n number of sources, you would analyze the circuit n number of times because you're breaking up the circuit into n number of parts. Okay, every circuit is independent of the main circuit. Okay, every circuit is independent of the main circuit. So for every single quantity, you have n number of quantities to add up. So here I say that RT would be the sum of R1, R2, R3 all the way to Rn. R represents either voltage or current, and then T is the total sum of all the sources that are present in the circuit. So it is 1 plus 2 plus 3 plus all the way up to n number of sources. Okay. So the purpose of superposition is to break up a circuit into smaller, simpler circuits. So our analysis techniques are simpler. But you can see where it gets time consuming and laborious, right? If you have 2 sources for every single voltage and current, you have to perform 2 separate analyses. If you have 3, you have 3 analyses. 4, you have to do 4, and so on and so forth. And this is for every single quantity in there. And so it just multiplies exponentially. Obviously, it is depending on the circuit, of course, it would be simple, but time consuming, so highly inefficient. Again, as an engineer, you have to decide which technique you wish to use. Now, when we say analyze with only one source active at a time, we change the circuit. So if there are n number of sources, we take source 1, whether it's a voltage or current source, does not matter. Superposition applies equally to all. So we just take one source, make that working. All other sources are reduced to 0. So there are 4 sources in the circuit. You only have the first one active. You reduce all the other 3 sources to 0. You only analyze with one source working at a time. Reducing a source to zero means replacing it either with a short circuit or an open circuit. The concept comes from this. Let's say we have a voltage source connected between points A and B. And this is Vs. So voltage measured between A and B is simply equal to the source voltage Vs. So now I'm simply explaining why we replace it with a short and open circuit. Again, it's conceptual. Students should understand this, but it is more important to know how to do it. Okay. It's good. It's well and good if you understand why, but it's not important. The more important thing is you should know how to use it. Okay. So voltage source is replaced with a short circuit because the only way to obtain a zero voltage between 2 points is if both points are exactly the same potential. And the easiest way to do that is to run a wire between the 2 points. If you run a wire or a connection between the 2 points, they are now shorted together. If they are shorted together, VAB is zero because they are the exact same electric potential. Doesn't matter what that potential is, but it would be zero. Does that make sense? Okay. But again, more importantly, voltage source reduced to zero means you replace it with a short circuit. You place a short between the 2 points. And taking that concept and applying it to current sources, current needs a pathway to flow through. So if this is A and this is B, and you have current IAB flowing through that path, the only way to stop traffic from flowing, you have to break, well, you have to stop the flow of traffic. The only way to stop flow of traffic is to dig up the road. Not really. But the analogy still applies. Current needs a pathway to flow through. The only way current can stop flowing is if you break the pathway. So you replace a current source with an open circuit. And so this is A, this is B, open circuit, and this is short circuit. Yeah. Oh, I thought someone had a question. Replacing a current source with an open circuit simply means you take the current source out of the circuit and you just leave it open. That's it. And so that way, IS is equal to 0 volts because IAB is equal to 0 volts. Oh yeah, amps. Okay. Any questions? One important point, we can only reduce independent sources to 0, the ones that are enclosed in a circle, not dependent. Dependent sources are the diamonds. So remember from the first week of class. Dependent sources depend on some other quantity in the circuit. So a dependent source cannot be reduced to 0. Only independent sources, the circular ones, can be reduced to 0. And reducing to 0 means replacing a voltage source with a short circuit and a current source with an open circuit. Yes. Yeah, it's kind of part of the syllabus, but it's in my previous experiences, I've just found that it just causes a lot of confusion. But an example would be, since a student is asking about an example, let's see an example. First thing to note is a dependency can be on another voltage or another current in a circuit. So dependent source can be a dependent voltage source. It could be a dependent current source. It simply depends on its value on some other part of the circuit. Simplest explanation I can give is like a voltage divider circuit. If you have two resistors in a circuit, I could take this VR2 and I would be applying, let's say, Vs plus minus here. VR2 depends on its value for Vs. VR2 is, and simply you can apply voltage division and we can say Vs is R2 divided by Req. If Vs changes, VR2 changes. So VR2 depends on Vs for its value. And we could take this and we could apply it to some other part of the circuit, which is a real life application would be like a adapter for your mobile devices or for your laptop. Laptop has multiple parts in there. You have CPUs, graphic processors, memory, hard drive, and they all require different voltages. Okay. USB ports, what's the standard spec of voltage? USB port that is in a computer or otherwise, what is the voltage? We use USB ports everywhere. No, after the power outlet, yes, but the USB port that is in your computer, it's 5 volts. As digital logic, 5 volts. That's why USB ports are 5 volts. When first digital electronics came out, analog can take multiple values over a range. Digital is zeros and ones. Again, I'm veering into a little bit into electronics, which is EE321. Anyway, so it's either 0 or it's 5 volts. If it's 0 volts, we would say it's represented by binary number 0. If it's 5 volts, we represented binary number 1. That's where that 5 volts came from. So a laptop or a computer for that matter requires a 5 volt line for the USB ports. That has been the spec and standard for USB since the beginning it came out. But if you look at your laptop adapters, doesn't matter which company you use, it has a rating. It has a power rating. Pretty much anything that you plug in the wall has a power rating. Laptop adapters will tell you what the input voltage is and what the input current is. It'll also tell you what the output voltage is and what the output current is. The output voltage in this case is 19.5 volts. Okay, 19.5 volts. So a single line of 19.5 volts goes into your laptop, but a laptop requires 5 volts. It requires 3.3 volts. It might require like 10 volts for running a fan, perhaps. It requires multiple voltages. That's where we would use a network like this. You would take the 19 volts, you would break it down into multiple different parts, and each part would be a dependent voltage source. It will supply, example, it will supply 5 volts to a USB port, but that 5 volt source is dependent on the 19 volts coming from the laptop adapter. Does that make sense? So slight segue for that example for the dependent source. But when we get to electronics, there are larger representations, larger circuits where we use dependent sources to actually show and represent some components. Okay, but dependent sources cannot be reduced to 0. Okay, this is very important. Dependent source cannot be reduced to 0. Okay, coming back to superposition. So again, it's more important to remember this. You can have these two lines on your equation sheet for the quiz and for the exam. Okay, you can have those on your equation sheet. All right, let's look at an example for superposition. We are asked to find the current I2, which is right here, using the superposition principle. So let's first write out and set up our problem correctly. 5 ohms, 2 ohms, 4 ohms, and 2 amps. How many sources in the circuit? Only 2, right? So it's rather simple and straightforward. What I'm going to do is I'm going to note circuit A when Vs is active, and when Vs is active, it automatically means all other sources in the circuit are reduced to 0. In this case, the only other source in the circuit is Is, so Is is reduced to 0. If there was something else in there, another voltage source or current source, that would also be reduced to 0. Okay, only one source acting at a time. Meaning replace Is with an open circuit. This is an open circuit. R1, R2, R3, plus and minus Vs, and I have I2 coming down. But because this is circuit A, I'm going to note I2 as I2A. Okay. Again, the notation can be anything you want. It doesn't have to be exactly A or B. It could be X and Y. It could be Batman and Robin. Be anything you want. Okay, so let's see. What is the relationship between, well, look at the original circuit. What's the relationship between R2 and R3? They're in series because they're connected only at that junction point right here. One junction point, right? They're already in series. Before I begin my analysis, I could potentially reduce R2 and R3 to one single resistance. But I'm not going to do that, not for this circuit. Now that we have removed the current source, replaced it with an open circuit, what is the relationship between R1, R2, and R3? They're all in series. So the important point to note is that every single time you remove the sources or reduce all the other sources to 0, your circuit changes. So every time you should draw out the circuit and show that change. So if you are solving a problem using superposition, you have to be very, very careful, again, because the circuit changes. With the current source in there, it's a different circuit. With the current source removed, it's a very different circuit. And now you see the beauty of applying superposition, because it is a one-step answer. You can simply reduce R1, R2, R3 to Req, apply Ohm's law, and find the current that is flowing through that circuit. So I can say I2A is simply equal to Vs over Req and Vs Req is R1 plus R2 plus R3. So it's simply 10 volts divided by 11. Make sense? Now the circuit could change. I mean, this of course is an example, so it's rather simple. In the circuit changes in a much simpler way, and it's a one-step answer. But most circuits are not like this. So if you try to solve for a circuit, always make sure that you set up the problem correctly and you redraw the circuit for each and every single source, because the circuit is different. So always have to keep that in mind. Okay, so let's look at circuit B. And in B, I'm going to have Is active, hence Vs will be 0. So I replace Vs with a short circuit. Okay, replace Vs with a short circuit. So now my circuit looks like this. And this is very interesting. So let's see. And this time I will combine R2 and R3 together. This is R1. I'm going to call this R4. R4 is simply the sum of R2 and R3 together. And so that is, what is that? 4 plus 2 is 6 ohms. I2 is still coming down from the top. And now it becomes I2B. Let's also mark. Now the circuit has changed. Okay. I'm just marking the terminals across the current source as 1 and 2. And so I have and of course, since I've solved this before, I know what I'm going to use. But when you are looking at a new circuit, you draw it out, you take a few seconds to ponder over the circuit and see how it has changed and what analysis techniques come to mind. Okay, so take a look at the circuit. Take a look at the circuit and let me know what you see. What is the relationship between R1 and R4? Yes, indeed, they are in parallel. So we can see R4 is already in parallel with IS just because of the way the circuit schematic is drawn. But now, when the voltage source is reduced to 0, replaced with a short circuit, the other end of R1 is now directly connected to node 2. So R1 is also connected between 1 and 2, current source between 1 and 2, and then R4 also between 1 and 2. All three of them are in parallel. And noted by the current signs, IS gets to junction 2 and then gets divided. So you could apply, what could you apply? Current division. We can apply current division. No, but that's correct. Current division. We are dividing the current. So current gets divided. We could apply Ohm's law, find the voltage between 1 and 2. And if you have the voltage between 1 and 2, we can find the current for both paths. Or if you want to skip that step, we apply current division. Okay. So let's do Ohm's law first, then I'll show current division. Essentially, both are the same. So if I was to reduce the circuit to REQ, this is REQ. REQ in this case is R1 in parallel with R2 plus R3, which is R4. Is 5 in parallel with 6. 2 resistors in parallel. 5 times 6, 30 divided by 11. This comes out to be 2.73 ohms. So find voltage V12 is simply IS times REQ. That gives me 5.46 volts. So IR4 is simply V12 divided by R4. .909 amps. So again, if you do current division, you can just skip that step and apply current division directly, and you will obtain the exact same answer. But the job's not done yet. Yes. Well, you tell me. You noticed it, so you're on the right track. What is your conclusion? Absolutely. So IR4, if we note the current direction, is the opposite of our noted current at the beginning of the problem. which is I2B. So if they are in opposite directions, we simply note it with a minus sign. And so the actual value of I2B is be minus IR4, which should be minus 0.909 amps. Does that make sense to everyone? Again, you have to keep in mind that the current direction for IS was pointing downwards, and that's why it is minus I2B. I2B or I2 is already given to us in the original problem, in the original question. So we cannot change that direction. The direction for I2B is already given to us. So we have to note the original direction and keep that direction for the entire analysis, because that is already given to us. We cannot change that. So it's very important to note everything that is given to us in the problem. Okay. And so my actual value for I2 is I2 is a sum of I2A plus I2B. So it is 0.909 plus minus 0.09. Turns out to be 0. If we had neglected to note the direction of I2 as minus for current source, then our answer, instead of being 0, would be 0.909 plus 0.909. Again, every tiny little thing matters. Attention to detail, which if you look at any job description in today's world, we'll always say we need a team player who is also an individual worker, also attention to detail. And that's where attention to detail is tested and assessed in the university. Okay. So again, take a look at everything. Let me know if you have any questions. Any questions at all? Okay. Then I will do one last thing here, is show you how the current division would be applied and be rather straightforward. Current division, of course, states that when current passes through a parallel circuit, it gets divided, and a fraction of that current goes through each branch. And in this case, the fraction would be of IS times REQ over R4. IS is 2 amps. REQ is 2.73 divided by 6. So again, the same thing. This is from current division. One-step answer versus 2 equations. Again, if you're not comfortable with applying current division directly, you can absolutely use it by doing Ohm's law. See, when a problem asks for a specific method, you have to show that setup. But once you're done with the setup, you can apply other techniques inside that setup. Meaning, if I'm asking you to solve it using superposition, you should absolutely show me how you can break up the circuit into multiple parts. But then when you analyze each part independently, you can choose any technique you want. You can choose KVL, KCL, Ohm's law, current division, voltage division, mesh current analysis, node voltage analysis if you want, because some circuits cannot be reduced to one single resistance. So in that case, we apply NVA and MCA, which though kind of is counterproductive. If I wanted to apply mesh current or node voltage analysis, I would apply it at the beginning of my analysis. I wouldn't do it as part of superposition. All right, any questions? Any questions at all? So superposition has been introduced, it has been covered in class, homework has been assigned. You have 4 days to do 2 problems. I'll make it due Monday night. Mesh current analysis quiz on Monday. I will post an announcement by 5 p.m. today. You again have the entire weekend. I'm available all weekend long over Zoom. Also available in my office today until 5 p.m. If you can't make it to office hours, send me an email. I can answer via email or I can meet you over Zoom. It's fine. Okay. Mesh current analysis. Most of you have done the homework, but it's not due until tomorrow night. So grade should be updated on Canvas once you're done submitting it. All right, so this is the end of all the analysis techniques that we learned for this class. For resistive circuit analysis, capacitors and inductors are come later. So in chapter 2, we do not learn any more analysis techniques. What we do learn is the concept of equivalent circuits, just Thevenin and Norton equivalent circuits. And you don't have to write anything down here on this slide. I'm just explaining the concept. Okay. So all of the techniques we have learned so far, we will take those techniques and we will apply to a larger theorem or larger application of a theorem, network theorem. You're not learning anything new in terms of analysis techniques, okay? These theorems simply require the application of the techniques that we have already learned. All right. Students often mistake and they think that it's like a new analysis technique and they get like scared and everything. But I'm here to tell you it's not. Okay. All you're doing now is you're taking your techniques and you're applying as part of that larger theorem. So let's say you are a designer and your team has a project and your boss asks you to find the optimal value of R6 so that VR6 is within a certain spec, which is a real life scenario. It happens often, right? Even if you're a mechanical, industrial engineer, mechanical engineer, civil engineer, you might come across a circuit. You might have electrical engineers in your team, but you may be part of some part of the design. And so you are asked to find a value for R6 so that VR6 is within a certain spec. What do? You would assume a value for R6. You might have a starting point, perhaps, maybe or maybe not. But let's say you chose some random value for R6, you perform an analysis to find VR6. What analysis techniques come to mind? We just did superposition. So superposition is a possibility. We have 3 sources. Certainly we could do that. We could do mesh current analysis, or we could do node voltage analysis. But at the end of your analysis, you find VR6 is not going to work. So you choose another value for R6. And you'd have to perform that analysis all over again. And you'd have to keep repeating that analysis and calculations until you find the right value. Make sense? Right? So faced with this kind of problem, there was a French telegraph engineer named Charles Leon Thevenin. He postulated a theory. This was in the late 1800s. He postulated a theory and said that if you wish to analyze a circuit like this, if you wish to find a particular value for a component, what you could do is you could remove that component from the analysis, analyze the rest of the circuit independently, and you could represent that entire circuit as a voltage source in series with a resistor. In this case, in this example, it would mean you would remove R6 from your analysis, analyze the rest of the circuit independently, independent of R6, and you could represent that entire circuit with a single voltage source in series with a resistance. And this theorem came to be named after him. It was known as Thevenin theorem or Thevenin's theorem. And the circuit is named again after him. So it's known as Thevenin equivalent circuit. Again, it's not an analysis technique. It is simply a representation. So it is known as the Thevenin circuit or the Thevenin equivalent circuit. The out plus and the out minus, they don't mean anything except their notations. So out plus would be here. Out minus would be here. It could be A and B. It could be X and Y. It could be Batman and Robin. Doesn't really matter. Okay. R6 is connected here, but it's not part of the analysis, obviously. But representation, after we are done with it, we plug R6 back in. Okay. Few years after Thevenin, I think it was a few decades actually after Thevenin theorem was published, there was a engineer working for Bell Labs, telephony applications. And there we use a lot of amplifiers and current amplifiers. And so it's more useful to work with current sources. So he and his team used to work with a lot of current sources. So he postulated his own theory, which is actually derived from Thevenin's theorem. And he stated it is possible to represent that large circuit as a current source. Instead of a voltage source, you could represent it as a current source. And this time the resistor would be in parallel to that current source. His name was Edward Norton, not the actor, just share the same names. And it came to be named after him as Norton theorem and the Norton equivalent circuit. Yes. Well, that is what we'll look at next week. Again, this is just explanation of why we do all of this. And then, of course, R6 goes in here. Now, different authors and different textbooks and different papers refer to this in many different subscripts. You would sometimes see this referred to as VTH, which is Thevenin voltage. RTH would be Thevenin resistance. And IN would be the Norton current. The subscripts could change, could be VTH or uppercase VTH or just VT. And then of course IN or IN, uppercase, lowercase, as you know, as it may be. Sometimes the RTH, so the RTH remains the same for both. Thevenin resistance is the same for both circuits. But if you're simply talking about Norton circuit, sometimes RTH could be represented as RN, which is Norton resistance. But it is actually the Thevenin resistance in both circuits. Okay, in both circuits. You have voltage, you have current, you have resistance. What comes to mind? Ohm's law. So you got VTH IN times RTH. Sometimes you might think it's easier simply to find the voltage, Thevenin voltage and Thevenin resistance, and find Norton current using Ohm's law, but it depends on the circuit. It's not always possible. Sometimes it's easier to simply to find Norton current first. Okay, so let me explain why it is more useful to find the Thevenin equivalent circuit. Okay, Remember, I said if you want to find VR6, we have to perform analysis every single time, right? But now, what is the relationship between RTH, R6, and VTH here? What do you see? Absolutely, they're all in series. So I could represent a Thevenin circuit this is RTH, this is R6. And just as the example we saw of a dependent source previously, now R6 or VR6 is a one-step answer. It would be VTH, fraction of VTH. Again, this is from voltage division. Voltage across R6 would be a fraction of VTH, and that can be given by voltage division, right? Now you could take a million values of R6, but you program this equation in your spreadsheet, apply as many values as you want, it would give you a million answers within like a few seconds. Okay, one-step answer. Again, the important point is we had R6, we removed R6 from a circuit, we analyzed the rest of the circuit independent of R6, and we obtained that voltage source, Thevenin voltage, and the Thevenin resistance. Okay, R6 is not part of the analysis. Very important to remember that point. R6 is not part of the analysis. Okay, you're analyzing the entire circuit independently of R6. And this is assuming, of course, the rest of the circuit is not changing, which in this class it won't. Okay. So think over this. Let me know if you have any questions. Does the concept make sense? We are not getting into any of the any of the application yet. We'll look at that next week. Any questions? Any questions at all? Okay. Well, we'll look at the application and determination of REQ and all of that next week. But you have already done this before. RTH is nothing but REQ. VTH, you can use any technique you want, node voltage analysis, mesh current analysis, or superposition to find VTH, and the same thing for IN. So again, not a new analysis technique. Application of the techniques to determine the Thevenin and Norton equivalent circuits. Okay, a guaranteed 30-point problem in the final exam. It tests everything from chapters 1 and 2. If you have not yet look at the final exam page. It's been on Canvas since the first day of class. It has all the options available to students, and it also lists all the topics that students need to study and are under assessment for the final exam. Yes. No, as early as possible. I won't even look at it until like the finals, just the week before finals when I make the room reservation. Typically, I would say about I have 115 students across all 3 sections. I would say about 50 to 60% of the students choose to do the Saturday exam just so they can get it out of the way and then concentrate on their their exams during the finals week. So again, it's an option. It's not that students have to take it. The exams are all kind of similar. They will be different, but kind of all similar levels. So taking it earlier or later is not a problem. Okay, we'll end class here today. Quiz on Monday. Look for the announcement by 5 p.m. today. All right. I bid you a good weekend, and I'll see you on Monday. Again, if you have any questions, I'll be available all weekend long via email, via Zoom. I'll also be in my office, later. I might be stepping in and out of my office for a little bit, but again, send me an email. If I'm not there, absolutely send me an email as soon as you reach there. But between 1 and 2:30, I should be in the office. And I'll also be available until 5 o'clock. Right? See you.